So, hello everyone, and today I'd like to talk with you about Kubernetes and architectures. And by architecture, I mean CPU architectures. So, what we are going to talk today about will be first Kubernetes and architectures, obviously. Also, a couple of different approaches to complex environments, because when we are talking about multiple architectures, very quickly we end up with a fairly complex environment to manage. We will then move to how to create and manage multi-architectures images to then draw some conclusion on the whole thing. So, about me, I have been working on Linux or with Linux for the last 20-odd years, and I've been a Kubernetes user since 2016, so 7 years at this point. And I do work at the moment for Red Hat. But this topic is not about Red Hat's product, it's wider, because we are going to talk about what Kubernetes does or can do for you. So, Kubernetes and architectures. We are talking about CPU architectures, and we have a bunch of those for many reasons. So, some examples of very common architectures are x86, ARM, ARM64, Arch 64, PPC, and S390X. All those are supported by Kubernetes. There are many architectures in the wild. Those are a very small subset of all the architectures that are available, and mostly this is due to historical reasons. So there has been some product differentiation that some companies wanted to have, so they created their own architectures. But also, there have been different philosophy in the designing of CPU architectures. The biggest one is CISC versus RISC. So effectively, how much logic do you put in the silicon, and how much logic do you put on the silicon in software? So there are different approaches, obviously, to the issue now. Nowadays, the majority of architectures are a blend in between, because a lot of CISC architecture moved toward RISC, and then a lot of RISC architecture moved toward CISC. So we do have less that differentiation, but still there are historical reasons for many of those families. And I think the bigger question for us today is, are those architecture actually relevant for us today? So let's assume that we don't have any machines today. Is it relevant to have different or machines with different architecture, or it's not? So I would say yes, in one hand, it's relevant, because those architectures, due to their history, are very, very different. They have advantages and disadvantages. But also, in the other hand, it's also true that for majority of people, actually it does not really matter. Because if I am a developer and develop Python code, for instance, I will not care at all which architecture my stuff is running on, or very limited to the fact that I might be using some libraries that do depend on specific architecture. But as long as I don't do any weird architecture-specific optimization, every architecture is kind of the same when I write code. When I execute code, things are a little bit different. So, is Kubernetes multi-arch? Yes, basically. But what exactly does this mean? Officially, Kubernetes supports x86, MD64. Those obviously are the most common architecture to run Kubernetes on. The only difference why we call it x86 and AMD64 is that the x86 is the 32-bit version, MD64 is the 64-bit version. Now, nowadays, 64-bit is pretty much everywhere. 32 bits is still supported, but very minority of systems actually run it. The second option is ARM, ARM64, or Arch 64, as they call it. And basically, those are usually kind of the Raspberries or those kind of devices, but we are seeing more powerful devices as well. PPC, PowerPC, this is, at this point, an IBM only, as far as I know, architecture, so power system from IBM. and also S390X, which still it's an IBM-only architecture, mainframes systems. But the reality is that unofficially, also, there are a bunch of other architecture that Kubernetes gets built on, and you can, in theory, use them to run your stuff. Now, since the Kubernetes project does not officially support those architectures, there is no real test done for those architecture in the pipelines of testing and so on. So effectively, you might incur in weird bugs on those architectures. So it's not suggested to actually use those in production environments. But if you really want to, you can start testing it, and if then you donate enough hardware to either the Linux Foundation or you commit to actually run a bunch of pipelines on that specific hardware, you can also get your preferred hardware supported. And also there is the fact that we can run a Kubernetes cluster that is multi-arch. And by multi-arch, I mean that in the same cluster, you do have different architectures of CPUs at the same time. And I think this is a very interesting situation. So when I think about different architectures, I think about those in terms of like ways to move things, in the sense that it's very similar to cars, motorcycles, lorries, and those kind of things, that basically all are similar because they all allow you to move yourself or move something, but still they are different systems. So in my mind, there is this parallel between those two things, and we'll see a little bit later why. x86 and AMD 64, I think them as a car. Probably the car is the most used kind of motor vehicle in the majority of countries, and it's the default for many people. Those are by far the most used kind of CPU architecture, and fundamentally, they are present everywhere. You can find them in the cloud, you can find them in the data center, in your own system, wherever you want. Size-wise, we are talking about usually between 16 and 32 cores per system. You can reach 100 cores, yes, you can even reach higher count if you go on 4 sockets stuff, but that is fairly niche, and probably you're not going to run Kubernetes on that stuff. And this is a sys kind of architecture. So sizing about RAM, in theory you can reach the 12 terabyte. I don't think I've ever seen a Kubernetes system running on a 12 terabyte node, simply because those nodes goes exponentially more expensive than buying just 24 512 gigabyte RAM systems. So in our Kubernetes case, which is a scale-out kind of case, usually, it would make more sense to have more boxes, cheaper, than to have smaller and lower number but bigger boxes. Feature-wise, it's interesting to see the fact that x86 supports SMT2, which means that you can run 2 different threads on the same core, which means that the hardware is the same, but due to how scheduling works and the fact that the majority of functions do not use all the chips in the core, the scheduler can run 2 different operations at the same time on the same hardware. And it does have a bunch of extension, and this is due to the fact that it's a CISC system. So effectively, the logic is to have a lot more features within the hardware. So we get, for instance, AES encryption, decryption, video encoding, decoding, and all those kind of things. Moving to the second architecture, that would be ARM and ARM64. I think about those as motorcycles. They are smaller, slimmer, but still very good option for many use cases. So usually you can find them on smaller system, and nowadays they are also available in bigger system. Ampere is the biggest producer of big ARM CPUs. Very often you will find them in the edge, but nowadays you can also start to find them into the data center. So for instance, on AWS, you can start to find Graviton instances, which are basically, Graviton is AWS proprietary ARM processor. So effectively, we are starting to see more and more of those kind of CPUs around. They have less cores. So you might find 10 cores sometimes, but in theory, you can find 256 cores with the maximum Ampere ones, but the majority of systems that you will find on the field will be between 4 and 8 cores. Also, very often when they have 8 cores, a bunch of those cores will be low power cores, and then others will be high power core or high performance core. So effectively, you have a mix of high performance and high efficiency core. This, though, is a RISC architecture. So the idea is to have very few functions in silicon and then do everything else and all the transcoding of higher input spaces into software. RAM-wise, same here. You can find 8 terabyte systems. Those would be on Ampere systems. But usually, we are talking about single-digit gigabyte of RAM. So an order of magnitude less, or a couple of order of magnitude less than x86 systems. Feature-wise, very interestingly, there is no SMTP. And usually, they do have a hardware accelerators, but they are outside the CPU itself. So, for instance, on your phone, you will probably have an AMD processor, ARM processor, sorry, and it will have a bunch of accelerators to do video encoding, video decoding, and that kind of things, but they are not in the CPU. They are added as external accelerators, which means actually that different ARM producers will have different accelerators, and therefore you will need different drivers to manage those. It's very interesting the fact that compared to x86, the cost of the hardware is way lower. If we are talking about the medium hardware, let's call it this way. If you are looking at the top hardware, as always, it's way more expensive than the average hardware. If you compare the top ARM hardware, it's still less expensive than the top x86 hardware, but obviously you will also get different performances there. So PowerPC, I think them as a lorry, basically. They are big, they are expensive, but they do carry a lot more stuff. So this is a very good architecture for vertical scaling. So the goal is not horizontally scale your workload, but if your workload only vertically scales, can be a good solution. And also, due to their architecture, their power consumption is lower per unit of work, which does not mean that they consume less power in general, but if we are talking about the same amount of work, then they will have consumed less power to compute it. Also, where we can find them, usually in data centers, because we are talking about things that are, I would say, only racks kind of hardware. There are a bunch of hyperscalers that do provide those, obviously IBM Cloud being IBM the bigger producer of power systems, but also Google Cloud and Azure. And this, I think, highlights the fact that those systems are not just IBM's opinion on what can be useful, but are effectively very useful for many different use cases. Talking about performances, the average system would have between 24 and 48 cores, but we can see systems that are up to 240 cores. But more importantly, the RAM easily goes into the terabytes. So it does have a lot more resources than your average x86 box. I think it's also very interesting to notice the features that those kind of processors come in. For instance, SMTP8. So effectively, while the x86 was able to run 2 different threads on the same physical core, the PowerPC systems are able to run easily 8 concurrent processes on the same core. So effectively, even though the amount of cores is higher than x86, but not like super higher, if you count for that SMT8 difference, then the difference becomes huge. Because if you have 100 cores of x86 that have SMT2, that means that you have a total of maximum 200 threads at the same time, but that 240 multiplied by 8 is basically 2,000 potential threads at the same time. Also, they do support full encryption of data transit between the components of the system with no performance hit. And this is a very interesting feature for all those confidential computing or trusted execution environment systems, where basically you really want to ensure that, or you want to guarantee to yourself and to your customers that only your process is able to see your data, and someone else's process that maybe is running on the same machine is not able to see your data, and vice versa. An interesting also fact is the fact that if we compute the number of watts that those systems use and the power, the performances they give you, you will get a way better, higher performance per watt value, basically. And as said before, and as the Lori, I think, points out, we are not talking about lower total watts. We are talking about still a system that will consume a lot of energy, but if fully used, then you will get a better performance ratio. The last category is the S390X. And I put the bus. They are very big, but the fact is they are very specialized systems for very specific use cases. So this is an architecture that is meant to be used for vertical scaling. So effectively, this means that you expect to have not many threads, but threads that will consume a huge amount of resources, and that you will not be able to split them between different systems. Or maybe you can have, for instance, a database where you do have multiple threads, but they have to run on the same machine because they have to cross-communicate and to share a state. These are usually foundable in data centers. Well, they are always foundable in data centers because it would be very inconvenient to put them anywhere else. But as of public clouds, only IBM clouds have those. For the other clouds, you can do interconnect, or other clouds call it differently, but the concept is the same, and still get mainframes there as well. Core counts-wise, we don't have huge numbers, as we were discussing. The numbers are not that huge and not very different from Power, but they do have interesting features. RAM-wise, higher than Power, but still, it's not like 50 times more. It's probably 5 to 10 times more. Feature-wise, they have huge CPU caches. So just to give you an idea, on the die, you would have up to 2 GB of L4 cache. And then obviously L3, L2 as well. Consider that on average, an x86 system has 50 to 100 megabyte of total cache on the socket. So here we are talking about massively higher quantity of cache, which means that if your thread continuously need a big state, it will not have to switch to RAM every few operations. It will be able to have a way bigger state into the cache itself. And the caches are an order of magnitude quicker than the RAM, just due to the latency of it. They do support full encryption with no performance hit, so okay. Same thing as Power. They also have internal redundancy. So effectively, you can, for instance, remove one cage, basically drawer of a mainframe, and all the operation would move seamlessly to another one. So you will have a way higher, reliability of the whole system. They also can scale out to multiple systems. So as long as the systems are up to 10 kilometers apart, you can basically move the workloads and data without the workloads noticing. So the workloads gets migrated, without any issues. They also support a lot of different high performance accelerators, I would call them. And the interesting part is that those are actually physical boards that you can add to the motherboard as if they were PCI boards, for instance, into the x86 board. And you can pick and choose the ones that most fit the kind of workload that you need to do. And just to give you an idea, the AES one, they call it crypto something card. If you put the maximum number you can put into a mainframe, you will be able to get hundreds of thousands of certificates per second. Now, even if you are a CA, probably you will not need that kind of number, so probably no one will ever put that kind of cards into a mainframe. But still, you can get a lot of these things, and the big advantage is that all of this is completely offloaded from the CPUs. So effectively, you will have no overhead, computational overhead on those. An interesting fact is the fact that they do have direct networking within mainframes with no additional cost. So effectively, if you have multiple VMs into the mainframe, they can communicate as if they would be different processes on the same system. So they don't have to go through the whole TCP/IP stack up and down, but they simply would communicate directly. And IBM claims, let's put it this way, up to 80% more efficiency on at the same amount of operations. Now, this claim of IBM comes from a study that they did with their customers, so probably is correct, but I mean, this is what the vendor claims. And an interesting fact is that if we are working in a big company or a bank, very probably you will have a mainframe somewhere. And that mainframe also contains the system of record, which basically is where all the very critical information about your state is. And if you are running your workload very close to that system of record, also you will get a lot of advantages performance-wise. So there are advantages. Also, there are also disadvantages in this architecture, as all the previous ones. So with this, I have a few thumb rules that I want to share with you about how to think about those different cases. Because the reality is, when you have to go somewhere, maybe at a conference that is close to your house and that kind of things, you will pick up a car, easy done. But when you have to do something that is maybe a little bit more complex, so for instance, let's say that you want to move house, then maybe your car is not the best tool for the job. You can still do it with your car, absolutely, but maybe it's not the best tool for the job. So I think as different architecture in the same way, which is I might want to have a default, but for specific workloads, I want to think if that is still the best option for me. First of all, obviously, don't try to use all of the available architectures just because they are there. The fact that there is something does not mean that you should be using it. You should be using it only if you need it. I would suggest to use Arc for edge cases, and by edge I mean like field edge, like sensors or on floor kind of systems, and also for horizontally scalable stateless workloads. So just to give you an example, if you have Nginx works very well on ARM systems because it can spin up a very big number of threads. Every thread get their own core. They can be pinned to a specific core. And then from there, every thread probably is going to deliver in a completely independent way from any other core. Let's think about a CDN, for instance. You don't really, well, you do have to maintain a state, but that state, you can maintain it somewhere else into your CDN logic, and then at that point, it's just serving files. At that point, an ARM architecture would be more convenient, probably. PowerPC, I think them for highly vertical scalable workloads. So for instance, databases, those would be a big example because you can get a lot of space for vertically scaling your databases. S390 for systems that require very high resiliency or data collocation with your system of record. So obviously we are talking about a very specific kind of use case, but just to give you an example, on a cloud, usually you can find 4 to 5 nines of uptime. With a mainframe, you can go to 8. So if you need something that is highly resilient, probably a cloud is not the best option. And then basically MD64 for every other option. So if your workload is not something that is very specific, then MD64 is probably going to be the best option for you. So when you start to have a few architecture maybe, and I guess that majority of you will have a few architecture in a short while, it could be, you know, going on bigger system, power S390, or going to smaller architecture, ARM, for instance. I think many of you will be looking at ARM due to the costs that are lower on some clouds. You start to get to a situation where basically it becomes more complex to manage those environments because you have mostly two options: multi-clusters or hybrid clusters, multi-architectural clusters. So the multi-cluster option will give you a lot of different clusters to manage. And in the end, you will probably end up having a central management system for multi-clusters. So there are a few examples, open source, closed source, does not really matter. But the fact is you will need a higher level of abstraction over the cluster. And this is usually something that company already find as a need, even if they don't go the multi-architecture route, because still, if you start to have maybe one cluster for prod, one for test, one for dev, one for QA maybe, and then maybe you do have a few regions around the world, then very easily you will get in the tens of clusters, and you will start to have multi-cluster issues as well. My suggested option for multi-cluster management would be open cluster management. There are a bunch of versions of those, but I think it's a very good solution for this problem. It's not the only solution. There are many, but I think this is the one I would choose. The advantage of a multi-cluster strategy is that, in theory, you can easily reuse all your knowledge that you have on your current systems. But you do also have the disadvantage that you will get more system to manage. Because in the end, you will have, let's say, the previous example, 20 clusters, x86. If you start adding maybe ARM64, then maybe you will add other 20 clusters. So immediately you will double the amount of clusters you will have to manage. The other approach is the mixed architecture cluster. So effectively keep the number of clusters, but add additional architectures in every cluster. So the advantage is that you have less cluster to manage, obviously. And I don't know why, but sometimes my clicker does not click. The disadvantage is that you will probably still need some cluster management system because, as we were saying, even if you are talking only about one kind of architecture, you are probably already in the tens of clusters. So you are probably already thinking about this kind of issue. And also, potentially, is unsupported by your vendor. So based on where you take Kubernetes from, some vendors do support mixed cluster architectures, others do not. So you might want to have a check there. Some ideas about mixed clusters, because I think that mixed clusters are going to be the future, and because they do allow a lot of very interesting use cases. One example, and I know it's random, because no one would ever buy a mainframe just for this. But if you think about this, where is the whole state of your Kubernetes cluster? On etcd. As long as you have your etcd majority, or at least consistency, your Kubernetes will always be able to restore itself. As soon as you lose that, you are going to lose your cluster. So effectively, the idea of putting etcd on S390, which guarantees us that huge level of resiliency, would be a great thing. Another idea would be to have databases on PowerPC. As we were discussing before, PowerPC allows us to have that vertical scalability that x86 does not have. So it could be a nice thing to have databases there. So as you can see, when we break this limit of the x86 architecture to think about multi-architecture clusters, then we can start to think about those kind of things. So in theory, someone could write a script or a program, let's call it this way, that evaluates your workloads that you're running at any given time within your cluster, and then choose to move them from one architecture to the other if they have certain pattern of execution or performances or whatever needed. So I think this is going to be the way Kubernetes will move over time. We have already seen in the last few releases of Kubernetes, upstream, I mean the Kubernetes/Kubernetes project, the introduction of more and more mixed architecture kind of logics. So I think that long term, that will be the preferred choice of many customers, of many people. Now, if you have a mixed environment, and this can be mixed within your cluster, or a mix of different clusters that are based on different architectures, you start to have an issue with how container images are made, which container images are architecture specific. So effectively, you will need to create architecture images that are multi-architecture. Now, there are two issues or 2 points to think about when we are talking about multi-architecture images. The first one, obviously, is how do we store images? Usually, we store images into registries. Will my registry work? Will it not? Will I have to do something about this? And the second is how do you build those different images? So starting from the first one, store images, very, very easy. Today, the majority of container registry already support multi-architecture images. Because of how multi-architecture images are made, they are very clever, and therefore the cluster can be very stupid about the architecture part. So nowadays, I would say all, if not all, 99.9% of container registry out there already support correctly multi-architectures. Now, the other part is then how do you build those images? So the first option, the first point is to leverage your build tools, the ones that you are already using. I'm not sure which one you are using. Probably is either Docker, Podman, one of those. Those tools usually can support you. So an example, if you use Docker build, it's very easy. This is how you would do it. So usually you do the build. Here we have a slightly different way because we have to build the manifest basically and then create a complete manifest that is a hyper manifest based on the other manifest, one for every architecture. So as you can see, it's fairly straightforward. The only boring part is going to be the fact that when you do the first one, obviously, you will be building on an AMD64 image, the second one ARM, and the third one PPC. Or you can also put whatever you want here. But the point is that since you are going to run on a real machine, not an imaginary machine, that machine will have their own architecture. So as long as you build exactly on the same architecture that your underneath host is running, everything is easy. But as soon as you start to build maybe an ARM image on x86, then you do have a virtualization part in between, so you will get some performance hits. Now, also you can do something more complex and more clever, such as having a CI/CD pipeline where you have multiple builds happening at the same time on different machines so that everything is native. You can do it. It's slightly more complex also. If you're doing if you are using Podman, the tool will be Builder to create images. And basically, as you can see, the syntax is very, very similar. So effectively, you can do pretty much the same thing in the same way, also different commands, but the logic is exactly the same. So we have seen how we can leverage the build system that we are already using. My biggest suggestion, and this is not only about this, but more in general, but more specifically about those kind of complex builds, use automation. Don't rely on the fact that your user will build your images for the various architectures because, yeah, maybe you have very good users, but on average, you will get issues on that. Another option, if your build system does not support multi-architectures, you can use Docker BuildX. And basically, this is the syntax. Docker BuildX is like a higher level kind of builder built on top of Docker build. And here we can simply specify with -- platform all the platform that we are going to support, and then the tag, and to push, and done. It will do all the steps that we have seen before effectively, but they will be completely hidden from you. It will be just BuildX doing its stuff. So a few conclusions. Evaluate which architectures will better fit your workload, but do it without pre-assumption on how things should work, or we have always done this way, or those kind of things. Start from scratch. What is the best architecture for me? Then obviously, you then choose if you go for the best or maybe for the most known one. But still, I think you should have that evaluation, sincere evaluation beforehand. Second, design your architecture, your global architecture of IT architecture to accommodate multiple architectures, because very probably you will run multiple architecture systems within the next 5 years. And also start today to build for all the architectures that reasonably you are going to have in the near future in production. Also, if today you have only one architecture and you don't think that for the next 3 years you will have another one, just build for your the one that you have in production. But if you are already starting to think about maybe adding some ARM Graviton machines or some other kind of machines to your clusters, then start to build your stuff for all those architectures as well, because in theory everything works. But you should really test your application, because you might find weird edge cases for some specific application. So it's better to test it. And also have fun, because as said, I'm fairly confident that you all will manage multi-architecture clusters or systems in the next few years. And it will break a lot of things. So at least start with a positive attitude. A learning attitude, because it would be fun. Thank you. And if there are any questions,